Hello, welcome to Chapter 4 on reliability. So as you know from your own experience, tests in school don't always measure our true ability. There are discrepancies between true ability and measurement. And these discrepancies constitute what we call errors of measurement. So in testing, an error is not the same as mistake. There will always be some inaccuracy in any measurement tool. So as psychologists, our task is to find the magnitude of errors and then try to minimize them. Tests that are relatively free of measurement error are reliable. A test must have at least two qualities to be considered a good test, usually three qualities. So these three qualities are reliability, validity, and standardization. So reliability essentially means consistency or repeatability, stability. If we have a reliable friend, we can count on that friend, that they will do what they say. Okay, they're consistent. So reliability tells us how consistently a test measures whatever it measures. So if I came into the classroom with a rubber yardstick, it would more or less randomly shrink and expand. And so if I would measure all the desks with a rubber yardstick, we wouldn't get accurate measurements. So in testing, we don't have rigid yardsticks. To measure traits like aggressiveness, IQ, we have rubber yardsticks, if you will. And they stretch and underestimate traits, and they shrink and overestimate traits. So as psychologists, we need to determine how much rubber is in our measuring instruments, how much air or how much measurement air. Now, a test must be reliable in order to be valid, but not vice versa. A test doesn't need to be valid in order to be reliable. So your slide has a good definition of reliability. It's the extent to which a test is consistent over time and thus relatively free of measurement error. Classical test score theory assumes that each person has a true score that would be obtained if there were no errors in measurement. But as you know, measuring instruments are imperfect. Thus, the obtained score may differ from the person's true ability or characteristic. So the difference between true score and observed score is due to measurement error. Reliability is defined by using three assumptions. The first assumption is that each person to be described by the test has some fixed amount of the attribute of interest. Okay, and that's called the true score. So, for example, everyone is assumed to possess some true level of intelligence. The second assumption, every observation of an attribute contains some error. And the third assumption, any observed score reflects both true score plus error. So you see the observed score equals T plus E, true score plus error. Measurement theory assumes error is random. Thus, the distribution of random error is bell-shaped. We see the normal curve on the previous two slides. The center of the distribution represents the true score. Dispersion of scores around the mean should display the distribution of error. Standard error of measurement is the standard deviation of the distribution of errors for each person and tells us about the magnitude of measurement error. SEM tells us how much a score varies from the true score. So it gives you a range of possible scores. Toward the end of the semester, I'll be showing you some of the assessments I did on children, and I'll show you some of my reports. And in intelligence testing, you never give one IQ score. There's a range within which the true score falls. So you'll see how psychologists use SEM in reporting results of tests. The domain sampling model. We need to sample domains of information when we construct a test. It's impractical to use an entire domain. So, for example, you want to construct a vocabulary test of English words. Okay. If you used all the words in the English language, you would get a true score. But again, that's impractical. So we sample from the domain of interest to be practical in order to assess, for example, vocabulary or spelling or what have you. In doing reliability analysis, we're estimating how much error we would make by using the score from the shorter test of spelling or vocabulary as an estimate of one's true spelling or vocabulary ability. So error is the result of sampling. As the sample gets larger, as the test gets larger, it represents the domain more accurately, and thus we have higher reliability. True scores aren't available, so we estimate them. We randomly select items from a given domain, and the test should be an estimate of the true score. Different random samples might give different estimates of the true score. So, for example, you keep sampling the dictionary randomly with a test of the same number of items, and the distribution of scores should eventually be a normal distribution. We then correlate each test and find the average correlation of the various parallel forms of the test, and this average would be an unbiased estimate of reliability. Now, when we're looking at tests, we want to choose a test to use for a client. We look in the test manual, and we want a minimum of 0.7 for a reliable test. And what this 0.7 reliability coefficient means is that 70% of the variation is associated with true variation among those who took the test, and 30% is random. It's due to chance factors. Item response theory is a relatively contemporary technique that moves away from classical test theory. In classical test theory, we require the use of exactly the same test. In IRT, item response theory, we focus on the difficulty of questions that will help assess an individual's ability level. So I believe the GRE and some other tests you may have taken work like this. It gets a sense after you answer a few questions of your ability level, and then it will move you ahead to a question that maybe the person sitting next to you does not get because their ability level is different according to the test. So it's adaptive. It's an adaptive assessment measure that adjusts as the test taker is more or less successful on items. Now, the problem with this is it requires a very large bank of items and complex computer programs to adjust as needed. There are various sources of error. Error can come from time sampling, item sampling, from the test not being internally consistent, and it can be due to observer differences. So I'll talk about each of these four in the following slides. If the source of error is due to time sampling, the method we use for determining reliability is the test-retest method. So, if your observed score differs from the true score, this can be due to a number of reasons. Maybe you take a test while you feel sick, and so the test doesn't reflect your true ability. Maybe the room was cold. Maybe there were noisy conditions outside the test room. And so you give the test at another time and correlate the scores to give you an estimate of reliability. Test-retest method, is used for time-related sources of error. It does not evaluate errors internal to the test. It measures errors external to the test. Test-retest is only valuable when measuring traits that don't change over time. So, for example, intelligence. We wouldn't use test-retest for depression because it does change over time. If test scores are relatively stable across repeated testings, we have some basis for believing that the test is measuring in a consistent way. Now, there's some problems with the test-retest method. So when using test-retest, we must consider carryover effects. So for example, we might remember answers from the first administration of the test, and that will boost our score on the second administration of the test. The second is practice effects, one important type of carryover effect. So some skills improve with practice, and so we score better on the second administration because subjects sharpen their skills just by taking the test the first time. So, for example, a test of manual dexterity. So we need to be careful about time intervals between testing. If the time intervals are too close together, we can get carryover effects. If the time intervals are too far apart, many other factors may affect the score. For example, someone reads a book related to the material. Okay, with achievement test, if it's too far in time, children may have actually learned more. So how to deal with problems of time intervals? So we do a lot of retest correlations with different time intervals between tests. So when you look in a test manual, you want to pay attention to the time intervals. If the source of error is from item sampling, then we use parallel forms as the method for determining reliability. So parallel forms is also sometimes called alternate forms or equivalent forms. So the test constructor constructs two parallel or equivalent forms of the test, and this is used to address item sampling error. So if you construct a test to measure spelling ability, error may be due to the items you selected. So now we're concerned with sources of error internal to the test. So we can use parallel forms of a test, such as the aforementioned, to determine reliability. In constructing parallel forms, we use the same rules to select items of the same difficulty level. And usually parallel forms are given on the same day. So a person takes a test, let's say in the morning, and they get the parallel form of that same test in the afternoon. And then we use the Pearson product moment correlation coefficient to estimate reliability. We get an R value. Now, when given on the same day, we can assume the only sources of variation are 1, random error, and 2, differences between the two forms of the test. Now, the order of administration is counterbalanced to avoid practice effects. Parallel forms provide one of the most rigorous assessments of reliability. So as we move through the semester, you'll see that there are some tests that have parallel forms. But the problem is it costs a lot of money because it takes a lot of time to develop parallel or equivalent forms of a test. If the source of error is due to the lack of internal consistency in a test, we have different ways to assess for reliability. So split half, KR20, and alpha. And I'll talk about these in more detail in the next few slides. Because we seldom have more than one form of a test, we must estimate reliability from a single group of items, and this can be done by assessing the different sources of error within a single group of items in a number of ways. So the first method of evaluating internal consistency is to use split half reliability. So a test is divided into halves. Usually it's best to split the test into odd and even because sometimes tests become more difficult as the items progress. And so odd even is the best way to split. And we score these halves as two separate tests. And then we compare the score on one half to the score on the other. And we do this by way of a correlation coefficient. Now the problem is that this would underestimate reliability because each subtest is only half as long as the original test. So to correct for split half, we use a formula called the Spearman-Brown formula, and it gives an estimate of what correlation would have been if each half had been the length of the whole test. Before talking about the KR20 method, I want to say a few more things about the Spearman-Brown formula. It can also be used to answer questions such as, if I had a 60-item test whose reliability is 0.61, how long must the test be in order to get an R of 0.7, which is an acceptable level of reliability? Or if I have a 300-item test whose R is equal to 0.96, how short can the test be? to have an R of 0.7. We don't want to tire people out with long test items if we can shorten the test and still have good reliability. Now, the problem with the Spearman-Brown, it assumes all items added or deleted are equal in reliability. And so we have another method for determining internal consistency and estimating reliability, and that is the Cooter-Richardson 20. It considers all possible ways of splitting the items in a test, so it avoids the problem of split half. And it's used in tests when items are dichotomous, so they're scored true or false, right or wrong, 0 or 1. Okay, and it's been found to produce reliability estimates that are about the same as the split half method. But again, its limitation is that it can only be used on tests that are dichotomous. Another method for assessing reliability is coefficient alpha, also known as Cronbach's alpha. So we can't use the KR20 for all tests because some tests, such as personality tests, aren't scored right or wrong, aren't scored dichotomously, and we can't use them when items are given different weight. So Cronbach developed a method for personality and attitude test that had or produced a more general estimate of reliability, and he called it coefficient alpha or Cronbach's alpha. And it provides the most conservative or general estimate of reliability. So it gives you the lowest estimate of reliability. So if Cronbach's alpha is high, you can assume the test is reliable because the lowest boundary of reliability is high. And so reliability will never drop below alpha. But what if you get a low coefficient alpha? It only tells you the lower boundary of reliability. The actual reliability may be much higher. When items in a test do not measure the same trait, the test will not be internally consistent and thus will get a low reliability coefficient. And so this is the time we want to use factor analysis when the test contains more than one trait. Okay, so by using factor analysis, we may find that the test is actually assessing two factors, aggressiveness and assertiveness. The reliability of each subscale may be quite high. However, the correlation between each subscale would be low. Another source of error is observer differences. So sometimes the source of error is the differences in observations. So for example, one observer may observe a baby smile 10 times when presented a certain stimulus, and another observes the baby smile 15 times. Thus, we need to assess reliability of observers, and there's a number of ways to do this. The first is to record the percentage of times that two or more observers agree. But a better way is to use the kappa statistic. It yields a bi-coefficient used for assessing the level of agreement among observers. So we call this inter-rater reliability. It's an adjusted index of agreement. How reliable is reliable? So professionals have concluded that 0.7 to 0.8 is acceptable in research. But in clinical settings, when we're diagnosing or predicting possible suicidality, we want it even higher than 0.7 to 0.8. So 0.9 in clinical settings is pretty standard. So what do we do if our reliability is low? So one thing we can do is increase the number of items on the test. Excuse me. And so we use the Spearman-Brown prophecy formula to tell us how many items we need to add to get to the desired level of reliability. And we can also use factor analysis and item analysis. So factor analysis, as you know, is a data reduction technique. So sometimes items on a test don't measure the given construct of a test. Okay, so for example, we may think we've developed a test of depression, but in using factor analysis, we find that we have items related to another factor, anxiety. So we eliminate the anxiety items, and that will increase the reliability of our test of depression. Okay, tests are more reliable if they are unidimensional. Okay, item analysis. Item analysis examines the correlation between each item and the total score for the test. So when the correlation between the performance or score on a single item and the total test score is low, then the item probably measures something different from the other items on the test, or that item is much easier or much harder than other items. Okay. So item analysis can be very helpful.